Hello and welcome back. In the previous lectures, we have looked at calculations of the heat work changes in a process, the internal energy and enthalpy changes for reversible processes involving ideal gas, as well as for irreversible processes that involve ideal gas. We've also looked at how to account for the temperature dependency of the specific heat capacity. We looked at Cp, but since for an ideal gas Cpig minus Cvig is R, essentially we can account for the temperature dependency of heat capacity for an ideal gas by integrating the appropriate equations, the polynomial expressions for Cp or Cv. So far, we did look at irreversible processes, but then the efficiency of a process has been given to us. This irreversibility, as we discussed earlier, is caused due to things like friction, the velocity gradients, and other dissipations that occur during the course of a process. And in general, these inefficiencies in a process, we are interested in knowing how these inefficiencies in a process can be accounted for, because ultimately that would give us how much work output comes out of a process. We would like to maximize the work output from a process, or work requirement is something we would like to minimize in a process, right? So if it is a process which involves work input, then we would like to minimize that work requirement. If it is a process from which we are extracting work, then we would like to maximize the work output from the process. And in either case, we would like to know how we can maximize or minimize the work, and that depends on the inefficiency or efficiency of the process, right? Usually, these are addressed by using a quantity known as entropy in thermodynamics. The word entropy is coined from a Greek word by Clausius, which means essentially transformation. So it acts as a measure to transform energy into useful work. It is a difficult concept, one of the most difficult concepts in thermodynamics when we encounter it the first time to understand and appreciate, partly because its influence on physical processes is very subtle, and we rely on heavy mathematical expressions to be able to understand this concept. So it sort of, to the beginners, it looks as an abstract concept, but it's, if you want to think about it, it is similar to thermodynamic variables such as internal energy or enthalpy, which are useful tools for us to quantify what is happening in a process. Same is the case with entropy. To begin with, let us start looking at a process and try to talk about what we mean by work and heat requirements for a process, or how much heat is converted to work, or vice versa. Let's take a very simple example. Let's say I have an ideal gas, right, in a piston and a cylinder assembly, right? I have an ideal gas. This is a piston and a cylinder assembly. This ideal gas in the piston cylinder assembly at 14 bar and 0.03 meter cube is the total volume. So because it's an ideal gas, and if I know the total number of moles, I can calculate the temperature, or vice versa. Let's say, for example, this ideal gas has 15 moles in this assembly or system, and the temperature turns out to be 336.8 Kelvin. Now, if I allow this ideal gas to expand in a process such that the pressure halves, pressure falls down by 50%, the temperature, it's a closed system and it's still 15. We're going to take an isothermal process, so the temperature is still going to remain the same. All I'm doing is I'm allowing the pressure to fall by half to 7 bar, which means the volume is going to double. The total volume is going to double to 0.06 meter cube. So we have double the volume, everything else being the same, the pressure is going to reduce by half. Now, if this is the process, this is an isothermal process for an ideal gas. So as we have done earlier in the previous lectures, delta U is going to be 0 because this is an ideal gas. There is no temperature change. Q is going to be minus W. It's going to be the integral of P dV. And that turns out to be 29,112 joules. If you run through the calculations and get the number right, the way we did it the last time, essentially this is RT by V. Temperature is constant, so it will be RT ln V2 over V1, and then we can get the final number. So the total work output from the process is 29,112 joules, right? How much is the heat that we need to supply to get this work done? Q is also equal to 29,112 joules. The system has lost work, so W is going to be negative of that, this many joules. So although it looks as if all the heat is converted to work, which is true, but if we want to run a process, a cyclic process out of this, we also need to note that the system conditions have changed, right? So the only effect of this process is the effect of this process, or if I want to write the effects of this process, then the process has doubled the volume of my gas, and it has also produced a work equal to 29,112 joules, which is also same as the heat exchange. So these are the effects of my process on the system as well as the surroundings. We have supplied this much energy from the surroundings to the system. The system has produced so much work, and at the same time, the volume of the fluid inside the system, which we tend to call as the working fluid, has doubled. Now, so the effect, heat is converted into work, but at the same time, there is also another change wherein the volume of the fluid has doubled. Now, if I were to bring this fluid back to its original state, one of the ways to do it would be to take another isothermal process and extract heat out of the system, right? The same quantity of heat out of the system, then the work would be negative of this quantity, and then you will put the system back to the original state. But the net work in that scenario would be 0, because in one direction you are extracting work, in the other direction you're putting the same amount of work back on the system. So in effect, there is no net work produced from the whole cyclic process if the system were to go back to its original state. But then in real life, right, if we were to produce work from a system continuously, we need to build a process which we call as a cyclic process, right? So let's take an example. And we do this by using, and we call these systems which produce work as engines, right? So wherein we have a heat reservoir. Reservoir essentially is the term we use which is capable of supplying large amount of heat without change in the total property of the reservoir itself. So this E here stands for engine. So the engine gets some amount of heat from the hot reservoir at a temperature of TH for the fluid. It then produces some work, Ws, And after that point, it rejects some amount of work QC at a temperature of Tc for the fluid, right, to the cold reservoir. By doing this, so if I were to just absorb heat from the hot reservoir and do some amount of work, there is a change, like we have seen in the earlier example, in the conditions of the working fluid. And if I were to bring this working fluid back to its original state so that it can accept another batch of heat from the hot reservoir, and then I can make a cyclic process out of it, it has to discard some amount of heat to the cold reservoir. Let us say this amount of heat it discards to the cold reservoir, elevated at a different temperature, Tc will be equal to Qc. Then essentially what the engine will do is absorb heat at a temperature of QH from the hot reservoir and discard heat at a temperature Tc to the cold reservoir, and in the process it also does a work equal to Ws on the surroundings. So this is something we call as a heat engine, right? Now it's if I were to build a cyclic process using this heat engine, it's pretty straightforward. All we need to do is imagine a nice system which can do this job for us, right? So let's see if we can draw that system which can do this job. I'm going to build a piston and a cylinder assembly, right? So this is my cylinder, and then I'm going to put a piston in this, okay? And this piston is connected to some sort of a device, let's say a turbine or something like that, which is going to rotate when it moves and produce work, right? So this piston, movement of the piston is going to transfer into work. And now these are the walls of the cylinder. If I don't insulate them, they are going to continuously exchange heat with the surroundings. We don't want to do that. We want to do that only at when we desire to do it. We want to do it at some high temperature TH. We want to exchange or absorb heat from the hot reservoir, and at some cold temperature Tc, we want to discard heat to the cold reservoir. So let's say I have my cold reservoir on this side. This is a simple scenario which makes it easy for us to understand, right? And a hot reservoir on this side. And we would also, this is a pictorial representation, and it's nicely illustrated in a textbook by Professor Elliott from University of Akron and Professor Lira from Michigan State. So I would recommend you guys look at this representation for more details. But to quickly summarize this type of a device, this is what we have. So what I'm drawing around it, let's say this thing is an insulation. So we're going to well insulate this guy, right? Let's also put a break here. We're going to insulate the walls of the cylinder, right? So it looks something like this, a movable insulation which can be opened and closed at will, one for the hot reservoir side and another for the cold reservoir side. So when I open this, then you are exposing the wall, and then it can absorb heat. Let's take that out. Let's use a different color there just to make it easy for us. So when this insulation is open, right, or maybe I should just open it a little bit more so that it's easy to appreciate, right? So it looks something like that, right? And when this is open, this heat is transferred. When we want to isolate it, not exchange that heat, we're going to close that flap. And similarly, we can have one on the cold reservoir side. When need be, this flap at the bottom can be opened or closed. So this way, we have a piston and a cylinder assembly, and inside is my working fluid, right? And now let us say initially we start at a condition. This is easily represented on a plot, a P versus V plot, right? The initial state of the system is at a point A, and then A to B is going to be an adiabatic compression. That's my point B. This is my point A. A to B is adiabatic compression. And at B, we open the flap at the bottom, at the top, so that it can exchange heat with the hot reservoir at temperature TH. So let's write this down. A to B is adiabatic compression. Right? A to B is adiabatic compression, and B to C is expansion, QH at TH. It exchanges that heat isothermally and expands. So because it expands, the volume is going to increase, and we have something like that. This is B to C, right? And this happens isothermally, so the pressure is going to change slightly, and the volume is going to increase manifold. And then we have C to D, where we have an adiabatic expansion again to a temperature of Tc. And then D to A is isothermal compression back to its original state. So A to B is adiabatic compression from Tc to Th. B to C is isothermal expansion. C to D is adiabatic expansion, and again it comes back to Tc. And D to A is at the same temperature Tc. So this way, I'm going to highlight the temperatures at each of these states, right? So, and when these are isothermal conditions, in one scenario, we're going to reject heat to the cold reservoir. In the other scenario, it's going to accept heat from the hot reservoir. So this is how my whole process looks like, and then it becomes a cyclic process. By building a process using this piston and cylinder assembly, I can continuously produce some amount of work. We can very quickly do a first law balance on this process, right? And come up with the total net amount of work that is produced. Because it's a cyclic process, delta U for the whole cycle is 0, right? Which means W for the cycle plus Q for the cycle is 0, or this means W for the cycle is going to be negative of Q for the cycle, right? W for the cycle is negative Ws. That's the total amount of work it is producing, because the system is doing work on the surroundings. You get the negative sign, and on this side it is negative of it's gaining an energy of QH at TH and losing QC to TC, or Ws is going to be QH minus QC. To avoid the confusion of the signs, we usually put an absolute value on QH and QC, so that we get the signs we need on, or we get the correct sign convention on these quantities, right? and in fact on this side as well. We can remove the shaft work for now. Let's just call it as W for the process itself. So W for the process is going to be QH minus QC. This is the total amount of work done by the process. Now we come to the first statement of the second law. It turns out that no apparatus, right, or no heat engine has ever been built where the only effect is to produce W from QH, right? That is where W is only equal to QH, or where QC equals 0. We can never, it has never been built. This is an engineering observation. No apparatus has ever been built where QC can be equal to 0, so that all the work produced, or the work produced, is equal to the total heat absorbed from the hot reservoir, which is QH. So this is the basis for the first statement of the second law, right, which says that it is not possible that the only effect of any process cannot be to produce work from heat absorbed. In addition, the process there will always be some change either in the system or the surroundings, and because of that we lose some amount of work or heat that we have exchanged with the system, right? Now, another way of defining the same thing is through what we call as efficiency of the process. The thermal efficiency of such a heat engine is defined as the total amount of work we can produce over the total heat we have exchanged with the engine and at the hot reservoir. The efficiency is W by QH, right? And because by virtue of the first law, W we said is QH minus QC, the efficiency is going to be equal to 1 minus of QC over QH. Now notice what happens if QC equals 0, then efficiency will be equal to 100%. But we said it's not possible to have any process or any engine where QC can be 0. That's violation of the first statement of the second law. So there can be no process where the thermal efficiency can be 100%, or we can produce work, we can convert all the heat into work. So we know that there is some amount of heat that would not be possible to be converted into work. We can only convert so much. Then we ask the next question. If that be the case, what are the limits on the amount of work I can produce? It's fairly straightforward question to answer. But before we go there, let's talk about something known as a Carnot engine. A Carnot engine is something where all the processes occur reversibly. So if you look at the previous slide, right, if you look at this slide, we had 4 steps in the whole cyclic process. Each of these steps has to occur at a reversible condition. Because reversibility will reduce the inefficiencies in the process, the idea is that the Carnot engine will have the maximum possible thermal efficiency. Okay. That can be proved by taking a Carnot engine and a Carnot refrigerator together, right? So let's look at how we prove that a Carnot engine is the engine that will have the maximum efficiency. So let's take a hot reservoir and let's build an engine which will accept QH from the hot reservoir at a temperature of TH and then reject QC to the cold reservoir at a temperature of TC. And let's say this produces a work of W. By virtue of first law, QH minus QC is W. We're more interested in W, so let's just write this guy as QH minus W, right? It's the same thing. We just got rid of one variable instead of using the first law every time. Now, an opposite of this Carnot engine is what we call as a Carnot refrigerator. In a Carnot refrigerator, we actually reject heat to the hot reservoir right, and accept heat from the cold reservoir. We call this as a Carnot refrigerator. To be able to do that, instead of producing work, we have to actually do work on the refrigerator. Okay? We have to do work on this refrigerator. So let's say it needs a work of W again, and we can make these quantities different. This is QH prime, and by virtue of the first law, this will be QH prime. For a refrigerator, it will be QH prime, right, minus W. So you add these two quantities, it will be QH, right? So this is how it looks like. This is a Carnot refrigerator. Now let's say I have a Carnot engine and a Carnot refrigerator. In the engine mode, the efficiency is going to be W over QH, right? What we can do is we can actually combine these together such that the work coming out of the engine can be used to drive the refrigerator because it's the same amount of work. If we try to do that, imagine that we can use this work to drive the refrigerator because both these works are W's, right? They are the same quantities, so I can combine them and make it look like this, right? So if you now look at it, right, there is no external work that we are doing on the engine and refrigerator combination. There is no external work on this engine refrigerator combination, right? And in this case, it will be W over QH prime. Now, for a minute, so we can combine this engine and refrigerator together such that the W or the work produced by the engine can drive the refrigerator, right? So in one case, the efficiency is W by QH for the engine, and in the other case for the refrigerator, it is W by QH prime. The question is, can any engine have a efficiency that is greater than the Carnot engine, right? To answer that question, we can simply, like I said, combine these two engine and refrigerator combinations, and let us say that the efficiency of this heat engine we are considering here is greater than that of the Carnot engine. If that be the case, then what it means is that W, because it is simply the sign that is different in these two, engine and reservoir, what this means is W over QH is going to be greater than W over QH prime, right? Or this implies QH prime is greater than QH. So if I have any engine whose efficiency is greater than that of the Carnot engine, what it will do is that it will make QH prime, which is the heat that is rejected at the hot reservoir greater than QH. It's the same amount of work, right? If you look at the overall scenario, what it is doing then is that there is no external work on this engine and refrigerator combination, but then we are only driving or drawing some heat from the cold reservoir and rejecting it to the hot reservoir without actually doing any external work, which is again a violation of the second law statement. That is not possible, which means this cannot be true. So there can be no engine whose efficiency is going to be greater than that of a Carnot engine. So the maximum possible efficiency, thermal efficiency we can get is going to be that for a Carnot engine. So if the maximum efficiency is always going to be the efficiency of a Carnot engine. Otherwise, we can build a device which doesn't require any work but will be able to draw heat from a cold reservoir and reject it to the hot reservoir, which is not possible. There are other corollaries to it. We can also show that the Carnot engine or the efficiency of the Carnot engine is independent of the working fluid. So you can have any working fluid inside, it doesn't matter, the Carnot engine is always going to have the same efficiency, right? That again can be derived from the fact that you can combine an engine and refrigerator working with two different fluids, and if they have different efficiencies, then it will violate the second law, right? Because it is independent of the working fluid, right? I can also use an ideal gas as a working fluid, and the moment I use an ideal gas as a working fluid, it turns out that the efficiency can be rewritten in terms of temperatures and pressures, and you can relate it to the temperature of the fluid at the cold reservoir, or temperature of the fluid when the heat is rejected to the cold reservoir, which is Tc, and temperature where it accepts the heat from the hot reservoir, which is Th. So the efficiency of a Carnot engine is then going to be simply equal to 1 minus Tc over Th if the working fluid is ideal gas. You can derive this equation for an ideal gas, but then because we are claiming that it's going to be independent of the working fluid, this relation then is going to work for any fluid irrespective of the working fluid. Although the derivation itself is based on ideal gas, at the end of the day, Carnot engine efficiency is always going to be 1 minus Tc by Th, and it will be independent of the working fluid. And finally, this is the efficiency of a Carnot engine. For an irreversible process, this is the maximum efficiency we can achieve in any engine. For processes or engines which are irreversible, the efficiency is going to be even lower. So this is the maximum limit we are imposing on the thermal efficiency for a particular process, right? And when will this efficiency be 1? So the efficiency of a Carnot engine is going to approach 1 when Tc is going to be 0, when we can reject the heat to the cold reservoir almost at 0 Kelvin, or when Th approaches infinity. In either of these two cases, when we have a very high temperature or a very low temperature, we approach a thermal efficiency that is equal to 1. Otherwise, it's going to be limited by this expression here, which is 1 minus Tc over Th. So this is the summary of second law, a Carnot engine, and then the thermal efficiency for a Carnot engine. Let's quickly look at one example problem based on these ideas, right? We have a Carnot engine that is operated between 750 and 300 Kelvin. First question is, what is its thermal efficiency? And if it produces 95 megawatts of work, what are the rates of heat absorbed from the hot reservoir and heat rejected to the cold reservoir? Okay, let's see if we can answer this question. It's a pretty straightforward question once we understand the concepts we discussed a minute ago. Like we said, the thermal efficiency of a Carnot engine is going to be 1 minus Tc over Th, right? In this case, producing work. These are rates of work, so let's use a dot there. This is QH dot, this is W dot, and this is QC dot. And we are rejecting heat to the cold reservoir. We're accepting heat from the hot reservoir. The efficiency is 1 minus Tc by Th. So this is 1 minus, the cold reservoir is at 300 Kelvin, the hot reservoir is at 750 Kelvin. So the efficiency is going to be 0.6. So when we operate a engine between 300 and 750 Kelvin, the Carnot efficiency is 0.6. So the maximum efficiency, thermal efficiency we can get for operation between these two temperatures is 0.6. In reality, if the process is irreversible, then the efficiency is going to be even lower than this value. Now the second question. We know the work produced. W dot, the rate of work produced is 95 megawatts or 95 megajoules per second, right? And we want to know how much heat is absorbed from the hot reservoir and how much is to be rejected to the cold reservoir. We know that the efficiency is given by the expression W, amount of work we can produce, by the amount of heat that is absorbed. It can also be for the rates, ratio of the rates of these two quantities. So because our efficiency is 0.6, then it's going to be 95 over QH dot. So we can calculate then QH from this expression directly because I already know the efficiency of the Carnot engine. So QH dot is going to be 95 over 0.6, which turns out to be 158.3 megajoules per second. Since by virtue of the first law, W dot is going to be QH dot minus QC dot, we can calculate QC to be QH minus W, or 158.3 minus 95, which happens to be 63.3 megajoules per second. So then the three quantities I'm looking at are an efficiency of 0.6, heat accepted from the hot reservoir is 158.3, and heat rejected to the cold reservoir is 63.3. So that 0.6 is the upper limit. That's the maximum thermal efficiency I can get for any engine that operates between 300 and 750 Kelvin. Now let's look at another problem. We have the same scenario as earlier, but then this time the engine is irreversible. It operates with an efficiency of 0.35. Earlier we had a Carnot engine which operated with an efficiency of 0.6. This time, because it is irreversible, the efficiency is a little lower and is about 0.35. Now we want to calculate the work produced and heat rejected if QH is same as in the earlier problem, right? So we have the same scenario, but then QH is same as in this case. It is 158.3 megajoules per second. So let's write that QH value since it is same as in this previous problem. What we are given then is QH is 158.3 megajoules per second, and the efficiency this time is 0.35. If that be the case, we want to calculate QC and W. It's again a pretty straightforward application of what we have seen so far. Efficiency, as we have defined, is W dot over QH dot. So we're interested in calculating the work produced. That's W dot is going to be the efficiency multiplied with the QH value, which is 0.35 times 158.3, or this turns out to be 55.42 megajoules per second. Now notice what happened to the work done. The process is irreversible and the work done is only 55.42 megajoules per second. Earlier, for the same amount of heat absorbed from the hot reservoir, we have produced a work equal to 95 megawatts. But now because the process is irreversible, for the same amount of heat absorbed from the hot reservoir, we could only produce 55.4 megajoules per second of work. And QC dot, QH dot is going to be equal to W dot. So we can rearrange the terms to calculate QC dot to be 102.92 megajoules per second. What essentially we are saying is, if the process has become irreversible, I could produce less amount of work and end up rejecting more heat to the cold reservoir. I'm absorbing the same amount of heat from the hot reservoir, but because this process is irreversible, the work produced is lower, and then I end up losing more heat to the cold reservoir, or rejecting more heat to the cold reservoir. So in that sense, an irreversible process will output less work and end up wasting more heat that I'm absorbing from the hot reservoir. Let me give you one quick real life example of why people have started developing interest in all of these reservoirs and hot, accepting heat from a hot reservoir, rejecting it to cold reservoir. Most of this comes from development of heat engines, like I said, and power cycles. One of the easiest ways to appreciate the application of what we are looking at is in case of a steam power plant, right? What happens in a steam power plant is we have a pump, right? And then we put some liquid into this pump. This is our working fluid, and compress this liquid. So to be able to compress this liquid, we supply some work to this pump, WS pump, right? And compress this liquid to a high pressure. So we are at a condition A here, and we're compressing this liquid to a high pressure, wherein I'm going to add heat, QH dot, from a hot reservoir, right? Then it's going to accept heat from a hot reservoir. We fire coal, we burn fuel, and then that fuel is going to transfer heat at the hot reservoir to this working fluid, and then we can, let's say if the working fluid is water, then we make steam after we add heat. And then we're going to expand this hot steam, we're going to expand, and then during this expansion, we end up transferring some work to the turbine, which is what we will convert eventually into electricity. And after the turbine, we push it to a condenser, right, where we condense the steam coming out of the turbine or any liquid coming out of the turbine back to its original state, where whatever condition we have put it into the pump to begin with, right? So that's the condition D, and then we go back to the original state. So WS pump here, let's change these to a different color so that we can see them easily. QH dot here, WS turbine here, it's in the opposite direction, the system is producing the work, and then QC here, we are rejecting some heat so that we can condense the liquid, and then we push it back to the original state. So if you look at the conditions, so this will be at TC here, and this will be at TH here, right? So I have a liquid starting at A, which is compressed to a high pressure, same as that of the boiler, at B. And in the boiler, we add heat so that we make steam at high pressure, pH, and the temperature is going to be TH. and we use this steam to expand a turbine and produce some work. Whatever comes out of the turbine is going to be transferred to a condenser where we reject heat to the surroundings, condense the liquid, bring it back to its original state, and then circulate the working fluid through the entire 4 steps so that we complete the cycle in this manner. So this is how a steam power plant works, and if you want to calculate the efficiency or the maximum possible thermal efficiency for the process, I'm burning so much fuel, so which means it will give this, if I know the calorific value of the fuel, I know how much heat I can transfer to the working fluid, and for this heat I'm transferring to the working fluid, what would be the work I can produce out of the turbine? There is some consumption of work in terms of pumping the liquid, so WS pump. Everything else is the work coming out of the turbine through the entire process. And what would be the maximum value? I can answer this question by using the ideas we learned in the Carnot Engine concept, right? It's going to be 1 minus Tc over Th, and that would be the maximum value, but because of the irreversibilities in the processes and everything else that goes on, the real value is going to be much lower than the maximum value. So these are some of the applications of what we learned today in terms of the second law, the Carnot engine, and thermal efficiency of a Carnot engine. When we come back in the next lecture, what we are going to do is try to extend these ideas of the Carnot engine and the maximum efficiency, thermal efficiency in a process to develop a concept known as entropy, which is going to be useful in thermodynamic analysis of the processes. Thank you.